Right. Okay. Right. So I volunteered myself in the absence of anyone else rushing forward. So this is work that I did with Nick Brummel, who was here a few weeks ago. That is in this paper actually, so it's not super new, but it is to do with layering. In particular, it's to do with double diffusive layering. It's to do with a magnetic version of double diffusive layering. So there are all sorts of problems with double diffusive layering which we don't understand, which I'm not really going to go into in great depth. I'm more going to concentrate on this magnetic analogy. Okay. We heard in the meeting from Francesco Paparello about double diffusive layering. We heard from Paul as well. So I will say a little bit about all the things we don't understand about double diffusive layering, but I'm then going to kind of assume that it exists and to show you how it can be turned into a magnetic version of the problem. Okay, so normally, if I were to give this talk, I would talk all about layering at this stage as a thing that the audience didn't know about, but that seems a little redundant in this particular meeting. So I'll just say this is what I'm going to talk about, a bit of double diffusive convection and double diffusive layering. Then I'm going to explain what magnetic buoyancy instability is, in case you haven't come across it. Then I'm going to explain how it's related mathematically to thermohaline convection. Then I'm going to use the analogy between the two systems to describe how you can get layering in a magnetic system and why it might be of importance. Okay. So a very brief summary of double diffusive convection. So double diffusive convection just means convection with two components that diffuse at different rates. So the classic one is, if you like, thermohaline convection, heat and salt in the oceans, where the density ratio is about 100th. In experiments, often people use salt and sugar. In this one, sugar becomes the salt and salt becomes the heat. And it's a relatively small diffusion ratio. And in stars, for example, people talk about double diffusive convection, where you've got a gradient of composition, typically helium, and temperature. And in stars, this goes back, well, possibly even further than this. There's a famous paper by Dilk and Goff in '72 about how double diffusive convection can stir the material in stellar cores. Okay, and there's been lots of papers since.
Is there a meaningful ratio of diffusivity?
Oh, yes, sorry. I mean, small, probably very small, because temperature, yeah. I'm not sure exactly what number they use, but very small, yeah. Okay, some other things that people sometimes call double diffusive convection, but in my definition here are not. So magnetic convection, for example, is convection with an imposed field, but the classic magnetic convection, the density in Boutonesse, the density only depends on temperature. It doesn't depend on the magnetic field. So it's, although you've got another thing and the other thing is diffusing, it's not contributing to the density. Similarly with rotating convection, though they're often referred to as double diffusive. Okay, so the basics, there's two sorts of regime one can have. And it depends. So the density is always increasing with depth to be of interest. Okay, so they're stably stratified in that sense. They're not overturning, they're not density unstable, but you can have either hot, salty above cold, fresh, which is what's called the salt fingering regime. This is what Francesco talked about in his talk. Or you can have the other way around, cold, fresh above hot, salty, which is called diffusive regime. Astrophysicists call it semi-convection, same thing. In salt fingers, the instability is direct or steady. If you lift a blob from a cold, fresh region upwards, it will, of course, diffuse its heat very quickly and keep its freshness, and will can carry on up. Whereas in the diffusive regime, such a blob will fall, but can overshoot, and you get oscillatory instability. Okay. I'll say a bit more about that later. Actually, so today I'm going to talk about this regime, but we'll come to that, the diffusive regime. So this is just really, as I said, well, I will say a little bit about the mechanisms, but this is just to show you that double diffusion does indeed tend to form layers. So of course, there've been lots of experiments and lots of observations. Numerical experiments, fairly recent, interestingly, last 10 years or so. So these are simulations from the group in Santa Cruz, Stefan Stelmach at the time. And these are triply periodic cubes, okay? So the basic state has a linear, it's Boutonesque, it has a linear temperature gradient, it has a linear solute gradient, and perturbations are periodic in all directions, including the vertical, which is, well, it's not clear if that matters or not. I know Francesco didn't like that when in his talk, he said he didn't like those boundary conditions. They are typically what's used. They're obviously computationally super convenient. And of course, it stops any sort of boundary layer structure, but it's also, you could say it's artificial. And these are in the salt fingering regime. After a long time, it forms these layers. This is the temperature perturbation. And similarly, in the diffusive regime, okay, one also gets these layers. Okay. So what I'm going to talk about is magnetic layering. So I'm going to talk about an instability mechanism, which you may or may not have come across, called magnetic buoyancy, which in a certain guise can be considered to be double diffusive. So I'm going to explain what that certain guise is. Why might layering be important in magnetic buoyancy? So in the same way that in all of these things, one is bothered about transport through a layered system. And if you're modeling a stellar interior, then of course you have to parameterize heat transport and everything. So if there were magnetic layering, let's say in the radiative zone of a star that could affect transport, then that might be important. That's what people are bothered about astrophysically. So this is just another thing to add to all the many things that we don't understand about radiative interiors. Okay. And how I'm going to tackle it is to turn the magnetic system into the thermohaline system. Okay. Right, so this is what I'm going to go quickly through, because we've heard some of this, and but really all of these things are what we kind of are discussing at this program. Okay, so I would say it's unclear exactly the detailed physics behind layering in double diffusive systems. There have been a lot of different mechanisms put forward. They're nicely reviewed by Bill Merrifield in 2000, and there's a book by Timur Radko on double diffusive convection as well. So the first idea was put forward by Stern, what he called a collective instability of salt fingers. So this is so you've got salt fingers, which are narrow, and this is a long wavelength instability on top of that to destabilize gravity waves. And that exists, that instability does exist. It's not clear it's the dominant instability, and it's not clear that it leads to layering either. You might argue that the layering has got nothing to do with evolution from any linear state. These are just, they're on a different branch, a nonlinear branch, unconnected, and that you kick the system into layers somehow, and it stays there. Now, okay, this is a different. So the classical thermohaline convection is where you heat it from below, or the gradients are in the vertical. They're just dependent on Z to begin with. But of course, you can have horizontal gradients, and indeed you do. You do in the oceans. There's some nice, I think we saw these experiments of Huppert and Turner in possibly Detlev Losa's talk, where they have a block of ice, so you get horizontal gradients. And in Detlev's talk, he showed us his simulations of cafe latte, which he says is similar to the diffusive regime. I mean, what struck me about his movie, it's hard to tell, I suppose, in a movie, is that it seemed to be a very quick process. His layering formation from a horizontal gradient, as we'll see. Layering formation from a vertical gradient is a very slow process. So flavor of the month, in some sense, is this mean field instability of Radko, which Francesco Paparella discussed, which is all to do with the flux ratio. Okay, so the flux ratio of thermal to solutal flux. And it has to, you can get instability if it's a decreasing function of density ratio. It's a rather strange instability criterion in a way, because you have to do a bunch of experiments, different experiments, to determine whether this is true, rather than one experiment, as it were. Or, second flavor of the month, it could be a modification of the Phillips mechanism of stirring stratified flow. And Paparella explained nicely, in his view, that salt fingers, the whole point of salt fingers was that they gave rise to these clusters. And the clusters that were then the stirring. And the double diffusion at that stage had gone out of the window. You were stirring a stratified fluid. And that the instability was a means of getting some finite size stirrer. Okay. And that's an interesting idea. Paul has also looked at this in the context of double diffusion. So let me just say a little bit about the Phillips mechanism, because in some sense, I think this diagram is what we should try and understand in this workshop, in this program. So this is the simplest experimental setup. You have a stratified fluid and you stir it. So in these guys, Park et al., this nice paper in JFM, the stirring, it just goes linearly. It's just a rod which goes linearly, oscillates linearly. That's it. And it's a two-parameter. There's two parameters in the experiment. So there's the speed of the stirring. I suppose there's three in a way. I suppose there's the speed of the stirring and the size of the stirrer and the stratification. But there's two dimensionless parameters which you can write as a Reynolds number and a Richardson number. Okay, sort of Richardson number. It's not got a shear in it, but it's sort of Richardson number. And these are the results. So you've got Richardson Reynolds. All of these crosses are experiments. This is the layering regime. This is the non-layering regime. And this, I guess, they call marginal, unclear. Okay. And they have some nice, this is a particularly nice example of a staircase that's formed. And the crux of the matter, so we heard a lot about Phillips 2 weeks ago. We heard a lot about Barnforth et al. 2 weeks ago. And they have a nice model in which the sort of mixing length model, but the key is that there is an emergent new dynamic or scale. There's a there's a prescribed dynamic, there's a prescribed scale, the stirring scale, and there is an emergent scale. And it's the competition between these two which can affect the flux gradient relation, and hence you can get layers. Okay. So this I don't think is fully understood. This I think is, in some sense, what we should be trying to understand. Okay. Right. Back to thermohaline convection. So this is what we solve. Okay. Super easy. 2D. 2D is going to be crucial for reasons you'll see. Okay. It doesn't have to be 2D to get salt fingers and layers and all of this stuff. 2D is going to be crucial for the analogy that I am going to pursue. So it's Boosanesque. So you have a contribution to the density from the temperature gradient and the salt gradient. You have an advection diffusion equation for temperature and salt. Okay, it's incompressible. So you can write it as an equation for the vorticity, temperature, and salt. Okay. And there are 4 dimensionless parameters. Okay. Standard Rayleigh number, salt Rayleigh number, which in the literature is sometimes defined the other way, but this is how Turner, Uppert and Turner define it. For example, this is Prandtl number, and this one, which goes under various names, possibly Schmidt, but possibly not. Anyway, the ratio of the diffusivities of heat and salt. So as always, positive Rayleigh is thermally destabilizing. In this convention, positive salt Rayleigh is solutely destabilizing. Okay. So that's the simplest thermohaline convection system you can have.
So just briefly, J, please.
Oh, sorry. Yeah, J is the Jacobian. So J of Fg is dF by dx, dg by dz minus dF by dz, dg by dx. So this is U dot grad U, curl of U dot grad U. Z component of curl of U dot grad U, I guess. So this is the stability boundary under this convention. We saw this in another talk a few weeks ago, and it was flipped about this axis because you just convention and how you define RS. So salt fingers live down here in the thermally stable, solutely unstable regime. Overstable, what's called the diffusive regime or semi-convection, lives in the thermally unstable, solutely stable regime. Over here, everyone's unstable. This tiny little bit is just the residual effects of viscosity. That's why it doesn't go to the origin. And over here, everybody is stable. That's important for what I'm going to say. You might think it's obviously stable because the temperature gradient is stable and the salt gradient is stable. Okay. Now, so what's done, as I mentioned, what's done in numerical experiments is for convenience, and I mean, people would say, well, it's to assume periodic boundary conditions in the perturbations, even in the vertical. And you might say that's just as realistic as rigid walls. There are no rigid walls in the middle of the ocean. Okay. If you do that, there is no natural length scale. Well, there's no external length scale in the problem. There is a natural length scale, which is this one. Okay. So if you use that as the length scale, then these are the equations these are the equivalent equations. And it looks at first glance as if you lost a parameter. So the Rayleigh and salt Rayleigh have just combined into the ratio. Okay. So there's only the density ratio R0. So we used to have Rayleigh, salt, Prandtl, and diffusivity ratio. Now we've only got 3. And of course, the other one has not been lost at all. It's because in the standard way, the height is 1. And that's how you define the length. Whereas here, the length is defined here. So you've got your box size. Okay, so that's where the other parameter has gone. There is a hope that box size, if it's big enough, is not crucial. Okay, you have to be a bit careful with this because obviously the first and third quadrants and the second and fourth quadrants have the same density ratio. So you have to consider the signs of the gradients here. Right, so what is magnetic buoyancy instability? So magnetic buoyancy instability comes from a magnetic field in a compressible atmosphere that is dependent, the field is horizontal and dependent on height. Okay. First, so astrophysically, it's often called the Parker instability. The first paper on it is by Newcomb, with no astrophysical implications whatsoever, but actually a beautiful paper in which he looks at this through the energy principle. Now, I'm going to consider 2D modes because this analogy that I'm going to pursue only holds for 2D. Okay. So 2D in this context means the field line doesn't bend. So there's magnetic pressure, but there isn't magnetic tension. Okay. And you can work out, you can do a standard parcel argument as you would for convection, where you get the Schwarzschild condition. Then you get this criterion for instability. Okay, so the crux of magnetic buoyancy instability is that, at least for interchange modes, 3D, there are sneaky things to do with 3D, we're not dealing with that, is that B over rho must decrease sufficiently rapidly with height. Okay, so you've got a strong field underneath, which is kind of holding up, puffing up the atmosphere, and that's what that's the release of that is what gives rise to the instability. So you need B over rho to decrease sufficiently rapidly with height. This has no diffusion in it at the moment. Density, sorry, yeah. So B is the strength of the horizontal field. So you've got a field B function of Z in the X direction, let's say. Rho is density, function of Z. N squared is the standard. So the two competing gradients are a B over rho gradient and a P rho to the minus gamma gradient. And as I said, that's the crux of the matter. So Parker put this forward as a way of mechanism for promoting clumping of interstellar medium. It's often invoked these days as a way of getting magnetic fields out from the inside of the sun, for example. So how are we going to turn it into thermohaline convection? So magnetic buoyancy, so thermohaline convection is all Boussinesque, et cetera, et cetera. Magnetic buoyancy is inherently compressible, okay? And I don't really, and it's quite sneaky how you get it in. So the crux of magnetic buoyancy is that the magnetic pressure, okay, must affect the density. That's the whole essence of the instability mechanism. So you have like variations of magnetic pressure must be comparable to variations in density. This leads to this condition that the variation, the length scale along the field, LB, has to be greater than LB squared. This product of scale heights. Doesn't matter too much for where we're going, but I just thought I'd put this in. So how you can get, so you can just solve the full compressible equations, okay? Everything is there, but just as in all these things, it's nice to look for simplified systems like Boussinesque. So you can consider two parameters, B over H, okay, layer depth over scale height, and some measure of some thermodynamic measure like density variations or departure from adiabaticity, for example. And it turns out that depending on these, you can get 5, or at least, there are at least 5 asymptotically self-consistent reduced systems. Okay, so there's the anelastic system that you know and love. There's the anelastic system with a weaker field gradient and stronger field. And then, interestingly, there are 3 Boussinesq systems, okay? 2 of which have magnetic buoyancy in, and 1 which doesn't, which is sort of interesting. The standard Boussinesq equations of magnetoconvection do not have magnetic buoyancy in them. You might say, why is that? Okay, it's never really explained why that is.
So slow compared to the convectional alpine speed you have for perturbed pressure balance, including magnetic pressure, that immediately relates the density perturbation to the magnetic and temperature perturbation.
Well, there's nothing wrong with that, but that's not always the case, right? In standard Boussinesq magnetoconvection, that is not the scaling which taken. So then you have to say, what is it external, you know, what external parameters that I have under my control force you either into the regime you're talking about or into the Boussinesq magnetoconvection range, right? Because you can say, oh, well, one of them satisfies this and one of them doesn't, but these are not things that you can impose on a system. We'll come to that anyway. Right. I mention all of that because I'm going to study magnetic buoyancy under one of these magneto-Boussinesq approximations. So it goes back to Spiegel and Weiss, and the assumptions are standard Boussinesq things, layer depth small compared to all scale heights, including magnetic scale heights. We don't need to bother about this too much because we're going to be interchanges, so we don't even have grad parallel. And you have a plasma beta, okay? And this, you need epsilon2 to be much smaller than epsilon1, so that there's a separation of speeds in the alpha phase speed and the sound speed. Going back to what you were just saying, Pat.
You're back to the same.
Yeah. So to answer your question, in the magneto-Boussinesq approximation, the crux of the matter is that the total pressure variations are small. And that's true whether you do or do not have magnetic buoyancy. In the standard equations of Boussinesq magnetoconvection, this is achieved by both contributions to the total pressure, gas pressure and magnetic pressure, being of that size. In the magneto-Boussinesq, they are achieved by them being both bigger than that and offsetting. Now, whether that comes about, of course, is all to do with the plasma beta, which you do have at your disposal. Okay. So the essence is that, yeah, you have small total pressure variations, but they're not individually small. Well, they're individually small, epsilon2, but they're not as small as the product. Okay. So you have a balance, an offsetting at first order between gas pressure and magnetic pressure. So this is what the equations look like. Don't worry if any of this is not particularly clear. I'm heading towards an analogy with the equations that we've already seen. So this is the vorticity equation. This looks pretty good, right? This is, as before, temperature and magnetic pressure here. The induction equation, we can take the scalar product with B and we'll get an equation for magnetic pressure. You might think this looks a bit wacky because this is the induction equation and it's got density scale heights in it, right? And you might think there is no density in the induction equation. The induction equation, as we know, is just dV by dt, curl of U cross B, del squared B. So where on earth does rho come from? Well, of course, in the induction equation, there is a div U term. Div U is 0 to first order, but we're at the next order in this equation, in which div U is U dot grad rho, as it were, and that's where that comes from. Okay. And we have an energy equation. This would normally be delta T and delta P, but delta P and delta PM are equal and opposite. So they're looking So this looks okay, right? This looks like what we had before. This looks kind of like what we had before, advection diffusion of delta P. And this doesn't look like what we had before, because this is not advection diffusion of this guy, right? It's advection of this guy and it's diffusion of temperature. Okay, obviously we can force one into the other just by combining, and you combine them to come up with a different variable. So this is a mixture of the temperature perturbation and the magnetic pressure perturbation. Tau is the ratio of diffusivities. Okay. So this now becomes the key variable. And this becomes the key. This is not the plasma beta. This is the subadiabatic gradient beta. This becomes the key gradient. So it's a non-obvious analogy. Salt becomes magnetic field or magnetic pressure minus magnetic pressure, but temperature does not become temperature. You have this combination of the two. Okay. And that changes the problem, because from what I said earlier, I said the competing gradients are the entropy gradient, which is this guy. Beta here is the d by dz log p to the minus gamma, and the b over rho gradient. Okay, these are the two key gradients. And so you can have two Rayleigh numbers like this. So you might say these are the natural Rayleigh numbers for the magnetic problem. And then through the analogy, okay, salt Rayleigh number goes to magnetic Rayleigh number with just a prefactor. But thermal Rayleigh number goes to a combination of the two. So if you take that and then you put it onto this diagram, then it does look different. In particular, you get instabilities down here, which is kind of not where you might expect them, right? This is stable, stable. Quote, stable, stable. Okay. So, I mean, this whole quadrant, why do you get instabilities here? I mean, you can explain it by, it's the compressive effects of the magnetic field, heat a blob, and that can shed its heat and become unstable, overstable. So that's a bit surprising that at first glance that you would have any instabilities in this quadrant, right? You don't in the thermohaline case. You can get steady solutions here, even though it's an oscillatory instability. You can get steady nonlinear solutions, which Nigel and I looked at, Nigel Weiss and I, a long time ago. And the question I'm going to ask now is, can we get layered solutions here? Okay. So we're going to look at the nonlinear evolution of this system. Okay, so we actually solve the thermohaline equations and apply the analogy, just because thermohaline equations are in the nicest possible form. So these are quite small numbers numerically. They're smaller than other people have used. Because we're doing 2D, you can afford to go to have fairly small Prandtl number, fairly small diffusion ratio. So we're going to consider two cases. They're both in the first quadrant in the RA-RS plane. Of course, they have to be there if they're in the diffusive case. But one is going to be in the first quadrant in the RT-RB plane, and one is going to be in the fourth quadrant of the RT-RB plane. Okay. That's the resolution. That's the domain size. But say this is now at our disposal. I mean, this has become a parameter of the problem, the domain size. Okay. The hope is that. So this is a lot of. What does 100 pi mean? It depends on the width of those initial instabilities. So I'll show you that in a minute. It's a lot. There's a lot of initial instabilities in this domain. Well, I've said all that. Okay. So these are the equations that we're solving. We've now fixed these signs. Okay, we saw these earlier. So there's a dt by dz and a ds by dz there. So we solved them as thermohaline convection in T, S, and psi. Then we turn to magnetic buoyancy. So psi is just psi, but T in the thermohaline problem becomes this T star business, and T star, remember, is a mixture of T and PM. Salt becomes magnetic pressure, subject to a change of sign and a bit of factoring here. Density ratios do this. You know, you turn the temperature gradients into P rho to the minus gamma, this kind of thing. Okay. The driving gradients are entropy and B over rho. Okay, that's right. So this is what happens. So we start at rest. The preferred mode is what people call an elevator mode. These are, of course, oscillatory elevators. So they have no vertical dependence. And they are, of course, full solutions of the nonlinear equations, right? They have no u dot grad u. So they are, they just grow and will grow forever, but they're unstable. And so this is the growth of the oscillatory elevators. Then they become unstable and something happens. So since Pat likes pretty pictures, here's a pretty picture. So you can see the width of the initial elevator mode. So there's a lot of elevators in this problem, and then there's a nice instability. So this is the vorticity. There's only one component of vorticity: entropy perturbation, magnetic pressure perturbation. Okay, so this is the initial instability of the elevator solution. So this was first looked at way back by Stern, by Hollier. Well, she actually looked at the steady case. This, of course, is the basic state has two frequencies in it. It has a temporal frequency and a spatial frequency. So it's a Floquet problem. It's a double Floquet problem, actually, which is what one of my students looked at. So this is what happens. Okay, so the initial instability is in some sense just a means of getting somewhere completely different. So you get a solution which is well mixed. Okay, it's not quite homogeneous, of course, there's a background gradient. Okay, but at this stage, all memory of the initial elevator modes has gone. And there's no, there's also at this stage nothing which you would say is a layer. Okay. So this is what the gradients look like at that time. So they are essentially what they were at the beginning. They're linear and they're just a bit noisy, right? So this is the entropy gradient, the B over rho gradient, and this is the density. Okay, so they're just noisy linear profiles. Okay. So this is the case, sorry, I should say, this is the case that's in the first quadrant in the RT-RB problem. Okay. So this is the one which is, of the two cases I'm going to look at, this is the more unstable one, the more vigorous one as a linear instability. Okay. So this is just to follow on. So the plot I showed earlier of the energy was only up to T equals 600, which is here. So you get this instability which saturates, and then it just grows. Okay, eventually it will stop, but the kinetic energy just grows. And out over this long time, what happens is that layers emerge. Okay, so these are very noisy layers. This is a very turbulent system, but clearly there is some layered structure here. Okay, so these are perturbations in, well, okay, so the top row is the thermohaline problem, vorticity, temperature and salt perturbations. Then you use the analogy, this is the same, the vorticity, to get the entropy and the magnetic pressure perturbations. So the magnetic pressure perturbations look just like the salt with a change of sign. But these entropy variations look like a combination of temperature and salt. Okay. And then as time goes on, these just merge. Right? This is a common feature of, as far as I know, a common feature of every numerical experiment on layering. You get layers and they just merge and merge and merge until in the end you get one big step. Now, whether that's a consequence of these boundary conditions might be, because it goes, it goes against what we observe in the sense that in the oceans, there seems to be a well-defined vertical scale. In these problems, there is never a well-defined long-term vertical scale. You make your box bigger, it will just keep going. Okay.
What's the time scale?
Well, I mean, thousands of advection times. And thousands and lots of diffusion times. So, no, I mean, no, I don't really. I mean, what happens is that these, I mean, layer merger in this problem, these are so messy that they're destroyed by a particular turbulent burst. Okay. And so they're just doing this stuff until there is a particularly energetic bit, which you can see it here. So it's going to power through here. And once it's gone, that's it. So
associated with the big fluctuations you would see in your
sorry,
it shows the energy versus time.
Yeah. Yeah, that's right. And so, I mean, it's an interesting question what the time scale is, but I think you need some like statistical features of the flow, right? Just to describe the energy variations, fluctuations.
If that's some kind of rare event, I wonder whether there is some other scale parameter which separates the size of your simulations from the real world examples. So, for instance, if you imagine in coarsening that the rate of coarsening is exponentially slow in the mean spacing between the layers in some units, then you could imagine it being ever present in modest size simulations, but somehow missing beyond a certain length scale of coarsening. I think it's just
yeah.
Possibility.
Yeah. I mean, I think also that there is, I think the absence of another scale from the beginning. I mean, if you had a non-Boussinesq stratified fluid, then you've got a scale height, for example. So you've got another scale on which to exist, as it were.
It's clear that as the step size becomes larger, it takes more and more time for the mergers to happen. Initially, when the step sizes are small.
Yes. Okay. No, that is true. That is true. Yeah. So this is, this is just sort of carrying on. You can see that now we're down to 3, and now we're down to 2. And if we wanted, we'd be down to 1. But these are long simulations. Okay. So this is what you know, this is a more concrete demonstration of staircases. So, so these 3 times correspond to, so this is t equals 3,600. So it's very messy, but you know, so if we horizontally average this and put the background gradient back in, and again at these 2 times, what do things look like? Well, they look like this. So this is the entropy gradient, this is B over rho gradient, and this is density gradient. So actually you get this, the staircase is most obvious in the density. Okay. Now, what people are fussed about, or one of the things people are fussed about, is turbulent fluxes. So you can have, so in the thermohaline, it will be flux of temperature, flux of heat. Here you can work out the flux of entropy, for example, and it just increases. It's incredibly noisy, but it does just increase, which is what people always find. There is more, as layering goes on, transport of heat and salt, or whatever the relevant quantities are, just increases. Okay. Right, so we can play the same game at a different density ratio. So from a thermohaline point of view, you might think, well, it's just another place in the first quadrant, right? We're in the RA-RS. We've just looked at somewhere in the first quadrant. Boom, I'm going to look at somewhere else in the first quadrant. But from the magnetic buoyancy point of view, we're now in the 4th quadrant. Okay, so the 4th quadrant has 2, quote, stabilizing gradients. So something different has to happen, because in the case we've just looked at, this one is stabilizing and this one is destabilizing, okay? But if they're both stabilizing, how are you going to get staircases? Okay. So this is what happens. This is a nicer one visually, aesthetically. So this is less, and this is less vigorous as a linear instability. So layers emerge. They emerge in sort of patches. So whether you would say, you know, if this were the Radko instability, you would say that there was some instability with a finite wavelength, with a wavelength here. Okay, what actually happens is that it's not well defined in that sense, in that they start emerging. Of course, top and bottom doesn't mean anything, it's periodic, but they start emerging in certain regimes, and then eventually fill out all the gaps until you have this nice picture here. This is a super slow process. So here we've gone all the way up to this time, and essentially we'd had enough. So we did not pursue this through all its mergers and everything, because it's just so slow and so, you know, expensive to do. But now let's go back to this question of what happens to the profile. So this is the thermohaline case. Okay, so we're in the first quadrant, so we're thermally unstable. We're hot at the bottom, colder at the top, salty at the bottom, pressure at the top. Okay, that's what that regime is, and you get this nice staircase. So this is the staircase in the thermohaline case, corresponding to this. Here it's shown in magnetic variables. Okay, but the magnetic variables, the magnetic gradients, are both stabilizing. Okay, so the only way you can get, so how's it going to do it? How's it going to get convection doing its stuff in between the layers if the gradient is the wrong way. So what it does, it overcompensates, and so you do get backward facing steps here. So it turns, so it's an overall stable gradient, but in between the layers, it's convecting away, as it were, by unstable gradients and super stable gradients in the interfaces. It's sort of interesting that it configures itself to get into that state. And again, turbulent transport just increases, okay, as layers emerge. So what does it all mean? From an astrophysical point of view, this stable, quote, stable regime might be important in radiative interiors. Okay, it's not going to be important in convection zones. Convection zones are convecting like crazy by definition, and so that's what will transport all the stuff. It's got, if this matters, it's got to be in a convectively stable region. Okay. But you can, if you put the numbers in, you can, it's not inconceivable that this could play a role in stellar radiative zones. Of course, what we did, even though we had small values of the Prandtl number and the diffusivity ratio, they're not astrophysically small, of course, right? Astrophysically, these numbers are tiny. Okay. And it's worth saying that the problem of mixing in radiative interiors is horrendous and unknown. So this is taken from a paper by Jean-Paul Zahn. This was his view of mixing in radiative zones. Okay. And the problem with radiative zones is that anything goes and nobody wins. Nobody obviously wins. In the convection zone, convection wins. You don't have to fuss about anything else. You say it's convecting like crazy. I'm going to have a theory for turbulent transport by convection. Once you're convectively stable, then a whole slew of things come in of, rotational instabilities, breaking waves. This is just one more candidate. I'm not sure it's a candidate that everyone, we had enough candidates, but this is another candidate. But there is a nice paper by Busu et al. Trying to explain observations on the red giant branch and struggling. And what we have here would actually fits into what they need for this. But it's a very complicated problem. And so this is what we would say, though, is that magnetic field in radiative interiors is nearly always a brake on whatever is going on. It suppresses instabilities, typically, right? If you've got a flow instability, the magnetic field typically, not always, but typically suppresses it. Whereas here we're saying no, even in a radiative zone, magnetic field can drive the instability. Okay. Which is a different take on what's normally put forward. So all of this, of course, was pursuing an analogy. The analogy holds, in very strict sense, the analogy holds for 2D motions because the analogy really is between magnetic pressure and salt. In the full MHD system, you have magnetic tension. Okay, there is no equivalent of magnetic tension in thermohaline convection. So there's two obvious questions one can ask. Will it hold in 3D? Will it hold beyond the Boussinesq approximation? In 3D, I would say yes. So there's no analogy in 3D. You can't take the 3D thermohaline convection model and make an analogy. But of course, magnetic fields in 3D, it imposes a preferred direction. And so magnetic buoyancy instabilities, even in 3D, are long along the direction of the field. So there's still a strong anisotropy. So you might think, I would think, that the ideas carry through. As I say, it would be very interesting actually to explore this beyond the Boussinesq approximation. You have another length in the problem. If you were to do it, say, in the anelastic approximation, you have a scale height. And yeah, that I think is an important thing to look at. So I'll stop there. Thank you. And sharing as well. Questions? Bruce.
Comparing the two staircases that you saw in the case, they're much tighter than the case before. It also that the one is much more happening. The vertical scales.
Yeah, well, you're right. So yeah, the scale is way smaller. It's quite hard to, yeah, it's quite hard to define a scale at which these things first emerge. You know, they might be on an even smaller scale, and you can't really tell that they're layers. But you're right. When you get well-defined layers in the second case, they're on a much smaller scale, shorter scale. They're less turbulent because you're not so far into that regime. Everything is progressing more slowly. You say, yeah, well, mergers, we just didn't. I'm sure they would merge, but it would take forever.
Profiles superimposed on gray scale standard deviation of the density above each vertical level. So that's going to be fairly wide, like 5 cases, much more disruptive and fairly tight. My hunch would be the width of that standard deviation would say something about the rate.
Yes. Oh, it might. That's an interesting, yeah. Yeah. I think that's probably true. The more, yeah, a measure of the variation in them, yeah. EM.
Feel that these continuity drives these changes over time, and we have and we should have a modeling of the emergent and the stirring field, which is not satisfied very often. Turbulent scale, which increasingly by more
Well, I don't have a good feel for the stirring scale in this problem, particularly. I mean, in the sense that, you know, when Francesco showed his salt fingering regime, he kind of, out of his homogeneous stuff. Yeah, okay. I mean, I'm not sure I'm answering your question particularly. So, whoops. Oh, sorry. So in here, there's nothing obviously at a stirring scale that stage, but then, I mean, I suppose there could be if you analyzed it. Then I guess there's things, well, I mean, I guess it depends, doesn't it? If you think that this is to do with the Phillips mechanism, I guess there would have to be a stirring scale emerge out of this, which would then form, and then the emergent scale would be to do with gradients in that, but you know what? I'm not too sure what you're after. Mm. You mean let it evolve to a layered state and then map that somehow? I don't know.
Candidate for the emergent scale here. If you're stable in T, then it's something like the osmodots.
Well, I mean, it's yeah. I mean, it's something to do with one of the stable gradients, but
What if you're stable?
yeah, but you're always stable in density. That's the key thing. So it's something to do with that, but it's not obvious what the emergent length scale is. I mean, in the salt fingering case, I wouldn't say it was obvious. You can argue that it would. There's a plausible argument involving the density ratio. That argument didn't work in this case. I mean, Paul mentioned that in his talk. It's not, I mean, I would say it's not straightforward to turn the Bly arguments into double diffusion. And it's an interesting question. Is double diffusion just a sort of means to an end? You know, are there other instability? You know, if you had any instability of a stably stratified fluid, does it lead to stirring that leads to layering? You know, that was Paparella's take on salt fingering. Any more? Peter.
Well, just to be clear, so I mean, everything you said could be understood in the context of TS system. You said there are various subtleties about how you transfer a given magnetic system.
Yes.
Yes. But in some sense, if we wanted to kind of focus on the TS system, everything you said applies to that.
Yeah. In fact, we solved the TS system.
And,
there's lots of things we don't understand.
All these other questions about which quadrant you buy in.
Yeah, that's
sort of. You could say, I'm going to get rid of that. I'm not going to worry about it.
Hmm.
I'm going to focus on understanding what happened in the TS system.
yeah, which we don't understand. Yeah, that's right. But it's a simpler thing that we don't understand. Yeah.
And in these situations, you've got a sort of a long-lived configuration of layers. The energy is gradually creeping up.
It is. I mean, I think it will saturate it once you finally get to the, you know, the ultimate state, which is
the ultimate state allowed by the domain.
Yeah. Yeah. That's right. A bigger domain is a different ultimate state. Yeah. Which is obviously a drawback of, you know, there's something missing in that. Okay, lunch. Thank you.